A difference of two squares. Two learning targets. Factor differences of two squares. Now, that's where we're going to spend most of our time. But the goal, the big learning target, is number 8, to solve quadratic equations by factoring difference of two squares. All right, so if we have x plus 5 times x minus 5, does this look familiar? We use the FOIL method. We get x squared minus 5x plus 5x minus 25. We combine like terms. Those add together to give us a 0. We get x squared minus 25. So we're going to develop a method to start with x squared minus 25 and factor it to be x plus 5 times x minus 5. Same thing with one like this. All right? FOIL method would give you t squared plus 8t minus 8t minus 64. Combine the like terms in the middle. They combine to give us a 0. And we get this. So think of this way. Here we have a plus b times a minus b. A is just whatever the first term in the binomial is. B is the second term in the binomial, and we're not really paying attention to the sign for like the only time ever. Because these two binomials are called conjugates of each other. Two binomials that are exactly the same except for the sign between them are conjugates. C-O-N-J-U-G-A-T-E-S. Okay? And when we multiply conjugates, either as a plus b times a minus b, or down here as a minus b times a plus b, we will always get a squared minus ab plus ab minus b squared. Down here, the only thing different is I would have the plus ab in front, the minus ab then, minus b squared. You always end up with whatever that first term was squared, whatever that last term was squared, with a minus sign between them. We get the same thing down here. So whenever you have a plus b times a minus b, you always get a squared minus b squared. We're going to use that to factor a squared minus b squared. Now, factor, we know what that means. Differences, subtraction, minus signs. 2, we know how many 2 is. Squares, we know what squares are. X squared is a square, 25 is a square, 64 is a square, t squared is a square. And again, for the only time ever, we're not really all that worried about attaching signs to the term, are we? Okay? We need a and b with a plus sign between them and with a minus sign between them. All right? So, since a plus b times a minus b always equals a squared minus b squared, it's got to work the other way too, doesn't it? A squared minus b squared must equal a plus b times a minus b. There's no way around it. That has to be the way it works. I mean, that's the way equations work, right? If I write this on the left, because maybe I know that first, and that's my result. If I write this on the left, doesn't that have to be my result? It has to. That's the way equations work. Let's do some examples. Now, I've debated with myself over and over on whether I wanted you to rewrite things to fit our form of descending order of exponents. And they give us so many in this section where they do like they did here on the very first one, where they put the constant perfect square first and then the variable perfect square last, that it's going to kind of be a pain to rewrite them all. So we'll go ahead, as long as it's something squared minus something squared, I'm not concerned with the order. Okay? We'll try that, see how it works. So for number 1A, is 81 a perfect square? It's what squared? 9. Is c squared a perfect square? It's c squared. So that is a squared minus b squared, isn't it? It's 9 squared minus c squared. So the factorization has to be a plus b times a minus b. If that's giving you trouble, rewrite that 81 as 9 squared, and it's a little easier to see, isn't it? Now you see the a and the b written in the problem. Okay? You with me on that one? All right, let's take a look at 1b. Is 64g squared a perfect square? It's what squared? So let's go ahead and write that. And if you don't need to put that step, that's fine. This might help. So that's 8g squared. H squared is a perfect square. It's h squared. So we should get a 8g plus b times a minus b. Questions so far? All right, you look at these next two. Neither one of these is a difference of two squares. But we learned a while back, if you can find a greatest common factor, factor out a greatest common factor. What's the greatest common factor of 9x cubed minus 4x? X. So let's take out an x. What are we left with? Well, what's 9x cubed divided by x? 9x squared. What's negative 4x divided by x? Is what's left in the parentheses a difference of two squares? Yeah, it is. It's 3x squared minus 2 squared, isn't it? Now, writing that step right there, that's optional. It may help early on, and then you may want to abandon it after a while. So I've still got the x out in front. And what's my final factorization? 3x minus 2, 3x plus 2. Now, notice on these I put the plus in the first binomial instead of the second one. And on this one I put the minus in the first binomial. Is that okay? Yeah, it's okay. As long as your factors are identical, it does not matter which one which order you put them in. 1C makes sense? Blank stares don't tell me much. They make sense? All right, look at the last one of these four. Not perfect squares. In fact, it's not even a difference. What can I factor out of both those terms? Y. Now watch this. If I factor out a y, when I do negative 4y cubed divided by y, I get negative 4y squared. And then 9y divided by y, I get a positive 9. Those could be squares, couldn't they? Now, I got two ways to fix it. I can either leave that and then just write that, but instead, and that'll work, it'll be just fine. Your answer will look different than the answer I'm going to get, but they'll be identical, trust me. So there's nothing wrong with that, but instead what I'm going to do is, how about if I just factor out a negative y to begin with? If I'm factoring out a negative y to begin with, wouldn't that be a positive 4y squared? And wouldn't that be a negative 9? Y'all follow me on that? Now I'm in business. So equals, keep the negative y out in front. Is what's left in the parentheses a difference of two squares? Yeah. It's 2y in a parentheses squared minus 3 squared. And again, that step's optional. A is 2y, B is 3, A is 2y, B is 3, and what signs did I leave out that I need to put in? Opposites. Put a positive in one of them and negative in the other one. You think you got it? Any questions so far? All right. Now, this is kind of cool. This is one of my favorite things about differences of two squares. You may need to factor, I should have said factor, a difference of two squares more than once to factor completely. You may need to factor a difference of two squares more than once. So look at 2a here. Y to the fourth minus 1. Now that's not quite as recognizable as a perfect square as the ones we were looking at before, but isn't that the same thing as y squared squared minus 1 squared? Isn't y to the fourth y squared squared? So if it's not obvious, see if it's still a perfect square. Okay? Now, so A would be what expression? Y squared, and B is, well, B is 1, then we'll put a plus and a minus, because remember, we're not really attaching the negative to the B anymore, to the B squared, for this only. So A is y squared, B is 1, A is y squared, B is 1, put a positive in one of them, a negative in the other. Now here's why I had written, you may need to factor a difference of two squares more than once. Y squared plus 1 is not a difference of two squares. It's a sum of two squares. Sums of two squares are not factorable. Try it if you want. They're not factorable. So that has to stay the same. But isn't y squared minus 1 a difference of two squares? A is y, B is 1. So factor it again. A is y, B is 1, A is y, B is 1, put a plus in one, a minus in the other. Cool, huh? Any questions on that one? All right. Yes, you do. Yep. You have to do that. Now, let me take a little detour here for a minute. We're learning to factor differences of two squares so that we can use this factorization technique to help us solve quadratic equations. So, what if this was an equation? Move that down. So what if all along there had been an equals 0 here? What would we do? Well, we wouldn't do anything different. But now we would use the zero product property. We've got 3 factors this time instead of the usual 2 that are multiplied together to equal 0. So y squared plus 1 equals 0, or y plus 1 equals 0, or y minus 1 equals 0. Now these last two are easy to solve. If y minus 1 equals 0, we add 1 to both sides, we get that. If y plus 1 equals 0, we subtract 1 from both sides to get that. If y squared plus 1 equals 0, we would subtract 1 from both sides, because I've already told you y squared plus 1 is not factorable. And then we would try that square root, take the square root of both sides technique. Square root of y squared is y, plus or minus the square root of negative 1. Does negative 1 have a square root? What can you square that you get -1 as the result? Nothing. Actually, you'll learn next year you get imaginary solutions to that. You know why they're imaginary? Because they're not real. I mean, literally, they're not real numbers. Y'all got so much to learn. All right? But look at this. So here are our two solutions, and this one leads us nowhere. Okay? And that's how you use this technique to do the last learning target, to solve equations by factoring a difference of two squares. With me? All right. Let me move this out of the way. Ooh. That's what I meant to. Hey, look, they got the same answer I did. Who'd have thought? All right. 2B. You do it. Did you get what I got? All right. 4a to the fourth is a perfect square. It's 2a squared. Squared. Were you able to see that? And then b to the fourth is a perfect square. It's b squared. Squared. All right, so then I'm just following along what we did in 2a. So the first term in each binomial needs to be 2a squared. The second term in each one needs to be b squared with a plus sign between them and then a minus sign between them. What I wanted to do, I wanted to keep factoring that one, didn't I? Why not? Why didn't I? Because 2 is not a perfect square. Okay? If 2 was a perfect square, could I keep going? Mm-hmm. But it's not, so I can't. Questions on 2b? All right, 2c. Go for it. All right, hopefully you started off by asking yourself this question. Is 81 a perfect square? Yes, it's 9 squared. Is x to the fourth a perfect square? Yes, it's x squared squared. You don't have to write that down, do you? You have to identify the 9 and the x squared. So that's a squared minus b squared. So you get a plus b times a minus b. Okay, so far? The first parentheses is a sum of two squares. That's not factorable. The second parentheses is a difference of two squares again, isn't it? What squared minus what squared? What's A? 3. What's B? So 3 plus x times 3 minus x. Questions? A little of the frustration going away? I love differences of two squares. You can try all day long to factor that one if you want to, but you can't. Not just you. Nobody can. It's not factorable. Yes. If you can. Always be looking. Well, because is that a difference of two squares? Yes. So factor it. Okay? In theory, if we worked it out just right, you might have 7 or 8 steps of this where you keep getting the difference of two squares. So always look for it. How often should you look for it? Always. Will you always get it? No. I wouldn't even say you'll usually get it. But sometimes you will, so always look for it. Okay? All right, do that last one. Let's see if you got what they got. All right, I see some head nodding. That's a good sign. All right, 16y to the fourth is a perfect square. It's 4y squared squared. 1 is a perfect square. It's 1 squared. So a is 4y squared plus b, which is 1. A, 4y squared minus b, which is 1. The first parentheses is not factorable. If it was a minus sign between them, it would be, but it's not, so it's not factorable. But that one is, what's A this time? 2y. What's B this time? 1 again. So 2y plus 1 times 2y minus 1. Getting better? All right. And again, what would we do if there was an equal sign here? We'd set that equal to 0. That's not going to give you a solution because you get 4y squared equals negative 1, y squared equals negative 1/4, y equals plus or minus the square root of negative 1/4. Not in the real world. 2y plus 1 equals 0, or 2y minus 1 equals 0. 2y equals negative 1, y equals negative 1/2. 2y equals positive 1, y equals positive 1/2. Okay? All right. Sometimes more than one factoring technique needs to be used to ensure that a polynomial is factored completely. So, everything we've learned is fair game now. It might just be a simple, factor it using the T-chart. It might be factoring using the AC method. It might be factoring perfect square trinomials. It might be factoring differences of two squares. And what's the one technique we tend to forget? Greatest common factor. So let's look there first. Look at 3a. Is there a greatest common factor? Yeah, 2. So first let's factor out a 2. That'll leave us with y to the 4th minus 25. And y to the 4th minus 25 is a difference of two squares. What's a? Y squared. What's b? 5. So leave the 2. A is y squared. B is 5. Now, I know I can't factor y squared plus 5. What about y squared minus 5? Is that a difference of two squares? No. 5's not a perfect square. Is there anything else to do? No, we're done. That's the answer. Let's see if we got it right. Hey, look at us. We got it right. Okay. 3b. What's the greatest common factor? 6. Let's factor out a 6. What are we left with inside the parentheses? X to the 4th minus 16. Is that a difference of two squares? Well, certainly. What's a? X squared. What's b? Am I finished? No. What else can I do? The last binomial is another difference of two squares, isn't it? Leave the 6 alone. Leave the x squared plus 4 alone. That'll be x plus 2 times x minus 2. Let's see if we got it right. Well, isn't that something? You keep going until you can't. Yep. Rut-row. What's going on here? Perhaps factoring by grouping. When you have 4 or more terms, you might factor by grouping. Let's see how this one works out. So if I group the first two terms together, I can factor out a m squared. Good. So 2m cubed divided by m squared leaves us with 2m, and m squared divided by m squared equals 1. Then we group the last two terms together. Negative 50m minus 25m. What can we factor out? 25. What kind of 25 do you think you want to factor out? I'm thinking negative. Let's see how that works. Negative 50m divided by negative 25 will be positive 2m. And negative 25 divided by negative 25, positive 1. So we could factor by grouping because we have the same binomial in each place. Oops, that's not how you make it 2. So we have a GCF of 2m plus 1, leaving us with what? Leaving us with m squared minus 25. Are we finished? No. Can you factor 2m plus 1? Well, then what's the factorization of m squared minus 25? Yeah, that's what they got. And I want you to see this enough times. If there's an equal 0, why can I not write 2m? 2m plus 1 equals 0, or m plus 5 equals 0, or m minus 5 equals 0. I can solve all three of these. If 2m plus 1 equals 0, subtract 1, divide by 2. If m plus 5 equals 0, subtract 5. If m minus 5 equals 0, add 5. And I get 3 solutions. What are you going to try on that last one? See if you can do that one by grouping. Do 3D. Why didn't they keep going? Because you can't. Neither one of those binomials are factorable. Group the first two together, and you can factor out an r squared. That'll leave you with r plus 6. Group the last two together, and you can factor out an 11. Leaves you with r plus 6. So we have r plus 6 is our new greatest common factor. R squared plus 11 is our other factor. And neither of those are factorable. There's no greatest common factor. There's no difference of two squares. Okay? What if this one was an equation? We would say r plus 6 equals 0, or r squared plus 11 equals 0. We'd get r equals negative 6. Are we going to get anything from that other one? We're not, because we get r squared equals negative 11. R would be plus or minus the square root of negative 11, and there's no such thing as the square root of negative 11. Now, I feel like I need to tell you this. Actually, every equation has the same number of solutions as the last exponent on the variable. Trouble is, some of those solutions are imaginary. That's what's going on here on 3D. There's actually 3 solutions. Negative 6, positive square root of negative 11, and negative square root of negative 11. Trouble is, positive and negative square roots of negative 11 are not real numbers. Okay. Probably. Is that what it does say, error?